Hello, today I'm going to go over work and energy. And to begin, the definition for work is a scalar quantity that measures the amount of energy transferred through the application of force along the displacement. And this has three main equations we can use. So the first one is work equals force times displacement. And the unit is joules, and positive means energy gained, negative means energy lost. However, there's a limit on this equation where the force applied is not always constant. So this is a second equation we can use where if there's a graph force times displacement, the area under the graph is work done by force. And before I go over third equation, I just want to talk a little bit about what mechanical energy is. So energy can exist in many different forms like light or heat energy, but in AP Physics C, we only focus on mechanical energy, and they can also exist in various forms. But today I'm only going to go over linear kinetic energy and gravitational potential energy, and I'm just not going to talk about like elastic potential energy or like rotational kinetic energy because then the video is going to be so long. And these are just equation. So kinetic energy is 1/2 mass times velocity squared, and gravitational potential energy is just mass times gravity times height, and gravity is a constant, which is in physics you can use either 10 meters per second squared or 9.81 meters per second squared. It doesn't really matter. Okay, so this is our third equation. This is a work energy theorem where work is equal to change in energy, and I'll just go over some little detailed calculation where work is change in energy, which is energy final minus energy initial, which is kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial, and we can just simplify them into change in kinetic energy plus change in potential energy. Okay, so in physics C, like 99% of our question is going to be assumption that there's no like forces that there's no non-conservative force like friction or air resistance. So like mechanical energy of the object is going to be conserved. So energy initial is going to be equal to energy final. And usually energy total, easiest way to find it is kinetic energy final or potential energy final. This isn't always true because there may be some like potential energy left in the system while there's also kinetic energy existing. But for like this type of question where like the object is dropped, we can use energy total is kinetic energy final or potential energy final. So in this situation A, the velocity is 0, which means kinetic energy is going to be 0. And this is just equation just in case. Then our potential energy is going to be mass times gravity times height, which is 4 times 10 times 10, which is 400. Then we can know in situation C, where there's no potential energy, the kinetic energy is going to be 400 joules. In the system where the height is 5 meters, which is in the middle, kinetic energy and potential energy is going to be equal. Okay, now let's talk about non-conservative force. So in real life, like air resistance should be considered in something traveling in the air, and friction should be considered if something is like sliding across the floor. And these are taking energy across the floor. And this actually should be negative. So work done by air resistance is force applied by air times height and work done by friction is friction force times distance. Okay, let's go over just quick real life example. In assumption that there's no air resistance, for example, like a vacuum chamber, no matter how heavy the object is, they're going to reach the floor at the same time if they're simply dropped, because we can set up equation energy initial is energy final, and we can say 1/2 mv initial square plus mgh initial is 1/2 mv final plus mgh final. And then right after we drop, the velocity is almost zero, so we can just cross this out, and in the final, after it reaches the floor, there's going to be no potential energy because the height is zero. Then we know that mgh initial is 1/2 mv final square, and the mass gets cancelled out, which means the mass does not affect the velocity or time it takes for the object to drop. Okay, let's just go over the little practice problems. Okay, let's say there's a curling player and it's able to deliver an average force of 15 newtons onto curling stone that has mass of 16 kilogram. And if the curling stone moves on the sheet of ice at speed of 2 meters per second as it is released from hand of the curling player, over what distance does the curling stone in contact with the hand? And we can use two equations out of the three equations we talked about, which is work is change in energy and is force times distance. So we know change in energy is force times distance, and we know FD is, and when we did a detailed calculation, we know force times distance is changing kinetic energy plus changing potential energy, and because this object is in the ground, there should be no potential energy. So force times distance is 1/2 mv final square minus 1/2 mv initial square. And let's say beginning of the system is where everything was stationary, and the final system is when the curling stone moves at the speed moves at a speed of 2 meters per second. So which means there's going to be no initial velocity. So force times distance is 1/2 mv final square, and then we have to find the distance, so we can simplify by v squared over f, and we know all the value. So mass was 16 kilogram times velocity final over force, and that should be about 0.64 meters. Alright, this one's also similar, but okay, let's just read the question first. A car with initial velocity of 20 meters per second steps on a brake, causing it to slow down with constant acceleration. The coefficient of kinetic energy between the tire and the road is 0.25. How far will the car travel across the road before it stops? And there's a friction force, and then the final system's going to slow down, which means we're going to have to use non-conservative force. Okay, so think the easiest way we can approach is because force times distance, because we know, and work is change in energy, and then we can set up same as the previous question, FD is, and also for this one there's no height, so there should be 0, so FD is, oh sorry, it is work non-conservative due to friction force, so this should be negative times distance is change in kinetic energy, which is half mv final square minus 1/2 mv initial square, and final velocity is 0, so this should be cancelled out, and there's two negatives, so we can cancel out. Okay, is 1/2 mv initial square, and then we know this is friction force is mu Fn, and there's no angle, so Fn should be equal to mg. So I'm just gonna write mu mg is 1/2 mv initial square. Then we can cancel out mass, and we know all the value except for distance, so we can plug the value in. So velocity initial over 2 mu g. So distance is, velocity initial was 20 squared, 2 times 0.25 times 10, and that should be equal to about 18 meters. Alright, now let's move on to a little bit more challenging questions. Okay, this one's kind of introduction on conservation of energy. So there's a block on a ramp with angle of 30 degrees from horizontal is given a push which allows it to have initial speed of 12 meters per second. Given that there's no friction on the ramp, how high up the ramp will the block go? We can set up EI equals EF, which means potential energy initial plus kinetic energy initial is potential energy final plus kinetic energy final, and the initial height is 0, so there's no potential energy initial, and how high up the ramp will the block go, which means that at the maximum height the block is going to be momentarily at rest, so there should be no kinetic energy. So we know 1/2 mv initial square is mgh final, and we can cross out mass. So 1/2, so height final is v squared over 2g, which is 12 meters per second over 2 times 10, which is about 7.2 meters. Alright, this last question, I personally really like this question because you have to kind of use multiple concepts, and it looks difficult, but it is actually very easy. It's just a bit time consuming. So there's a professional ski jumper start from rest at the top of 15-degree incline and ski down distance of 200 meters. And the coefficient of friction between the skis and snow is 0.15, so mu is 0.15, and we have to find the final velocity of the ski jumper. Now, if there's a friction, so there's going to be work non-conservative. So let's just start by writing equation Ki plus Ui plus work non-conservative is Kf plus Uf. And then we can cross out there's no initial kinetic energy as well as no final potential energy. And let's write a more detailed equation. mgh initial plus negative friction force times distance is 1/2 mv final square. And then we can write that in further detail by writing negative mu Fn times d is 1/2 mv final square. And for this question, because the ski jumper is at the ramp, inclined ramp, the Fn is not going to be mg, rather it is going to be cosine. And let's just start plugging values we know. So we don't know m, so I'm just going to write m times 10 times the height. We know the hypotenuse and angle, so you can just write this as 200 sine 15 plus mu, and then our normal force is going to be, we know the coefficient of friction, so I'll actually just write 5 times 10, which is gravity, cos 15. So in this free body diagram, you can see this is mg and this is Fn. So this is going to be mg cos 15. 15 times distance, which is 200, and it is going to be equal to 1/2 mv final square, and we can cross out mass. And 10 times 200 sine 15 is going to be 517.64 minus 0.15 times 10 cos 15 times 200 is 289.77, which is equal to 1/2 v final square. Then I'll just multiply each side by 2, which is going to be v final square is 455.72. And if we square root that, we're going to get final velocity of 21.35 meters per second. Okay, so that's the end of the, quickly going over the concept of energy. I think this unit is really important because, as I said before, about 40% of MCQ for AP exam is going to be energy related questions, and many students struggle in this unit, but you must know this unit to pass or get 5 on your AP physics. Like writing just EI equals EF in your FRQ just gets you 3 points. So I would say this unit is really important, and that's mostly the reason why I went over this unit.